I guess before the quiz, we were looking at this this chapter on stresses and tractions and equilibrium. So very quickly, I'll revise some of the most important concepts. Traction was one. Traction is a point-wise expression of a distributed force per unit area. We also looked at an important relationship, the Cauchy reciprocal theorem, that says traction on a face n is equal to traction on negative of the traction on the face minus n, which follows straight away from Newton's third law. Another important property that we looked at was, or the relationship that we looked at was this Cauchy stress traction relationship. And I've been pointing out again and again that this relationship Tn is equal to Cauchy stress acting on a unit normal. This holds for any point in a deformable body, whether that point is inside the body or outside on the surface. This normal vector is something that you choose. Okay, so for example, if you go to a point inside a deformable body, at that point you can choose some surface passing through that point. Now that choice of surface is entirely up to you. That may depend upon a free body diagram that you are trying to draw. If you have a body, you are trying to draw the free body diagram of a part of that body, then at every point on the cut of that free body diagram, you would have to draw external forces acting onto at that point. So those external forces would be the tractions which would be obtained by taking the stress acting on the normal at that point. So that's a very important relationship to understand. We looked at this normal and shearing components, went through a bunch of examples of types of stress fields, looked at principal and eigenvalues and eigenvectors of these stress tensors. And I think that's about where we were with the equivalent representation with more circles. That's about where we were, I think, before the quiz. So what we'll do today is look at more conditions of equilibrium for deformable bodies. What we've been doing till now is just establishing what is stress, how is it related to traction. What we're going to do now is to try to figure out what would be the conditions or the equations that would be needed to be satisfied for a body to be in equilibrium. And keep in mind, when we talked about this equilibrium, we said that every sub part of the body must be in equilibrium for the whole body to be in equilibrium. So if I take some body, if I take any number of arbitrary cuts of that body, meaning I have a big body, I imagine parts of that body. I'm not actually physically cutting that body. Imagine any part, any arbitrary part of that body. You would be able to draw all the external forces acting on that body, both applied loads and tractions that have developed due to the stresses, and body forces. Under the sum of all of these forces, under the sum of tractions, applied forces, body forces, the body must be in equilibrium. And every sub part of that body must be in equilibrium for us to be able to say that that this holds. So for example, we'll again go to some point, and we'll consider some neighborhood, a finite neighborhood of that point. I'm not saying necessarily that this is a very infinitesimally small neighborhood. It could be big, a finite size neighborhood. And if I draw the tractions on that neighborhood of that point, those tractions will now not be constant over that infinitesimal surface. Those tractions would be varying, right, from point to point. So in order to ensure that this part of the body is in equilibrium, I would have to sum up the forces due to the tractions, sum up the forces due to the body force, and if it's any external tractions applied, I would have to sum those up as well. So all we are doing for this free body diagram is sum of forces equal to 0. So let's see how to write that out. we have 6 surfaces, or in general, any number of surfaces of a neighborhood of a point. So I'll write that as the total force on all these surfaces as T sub n dA integral over the entire surface of the body. Now, so let's say if I'm calling my body B, I'll switch here back to our original problem to kind of remind you where we were. This was our original body B. Okay, so maybe I'll name it here. This was our body B. The boundary of that body is what we are calling A, the surface area of that body. Okay. After the deformation, the body will take the configuration phi of B. Phi is the deformation map. Phi acts on the undeformed body B to take it to phi of B. Similarly, phi A would be the deformed surface area of the deformed boundary of that body. So when I say that we are doing sum of forces, should we write that, where is it? Should we write that integral over the deformed surface or the undeformed surface? Deformed surface. Equilibrium, of course, holds in the deformed configuration. In the undeformed configuration, when I apply the loads, the body hasn't deformed yet. It's not in equilibrium yet. So equilibrium we must write on the deformed configuration. So that's why I'll do phi of A. I need to do tractions dA integral over the entire surface of the deformed body that we are talking about, or deformed part of the body. That takes care of all the external tractions. I also need to add body forces to it. So body force is B, and I'll talk a little bit more about this body force, what this is. dV, and actually to be consistent here with our undeformed and deformed areas, I'm going to make it small a, because this is deformed area, and small v because this is deformed volume, integral over the volume of the deformed body. And so this accounts for all the traction on all the surfaces, all the body forces, and we set that sum equal to 0. That's the equilibrium condition that we need to satisfy for any deformable body. Here's what this body force is. We call this body force density sometimes. What does that mean? It is the distributed force per volume. So if you want to find the total force due to a body force density, you would have to multiply the body force with dV and integrate it over the volume of the body to find the total force, which is what I'm drawing here. Okay. Here's another example of a body force density. Let's say I have some object, say of constant density, then the total body force acting on it is due to Earth's gravity that's pulling each and every particle of this body downwards, right? The sum total or the resultant of all of those forces is the weight of the body that we draw at the center of gravity, like in a conventional free body diagram. But how do we get that weight? That weight is obtained by taking the volume of the body, multiplying it with the density to get the total mass of the body, and mass times gravity is the total weight of that. So weight is a type of a body force, but again, we can't say that the body force is a point load acting in the center of gravity. That point load is the resultant force that is resultant from all of these small body forces acting on the body. So this B is a body force density. Can you tell me what would this expression be for, let's say, this object that, and let's say our axes are x1 pointing this, x2 pointing in the vertical direction, x3 pointing out of the plane, and so obviously gravity would be pointing downwards. what would be this body force density for an object like this? Rho g, right? Density times acceleration due to gravity, that would be equal, and E2 minus E2, right? Rho g minus E2. Body force is a body force density is a vector. So you must specify both the magnitude and a vector for a body force. Very similar to traction. Traction is distributed force per area. Body force density is, of course, body total force per distributed force per unit volume. So that's what this is, and that's what would make sure that that some body is in equilibrium. What I'll do now is I'll use this expression. I know that Tn is also given by Cauchy stress acting on a normal surface of a body. So since I'm calculating all these tractions on the deformed surface area of the body, I know there should be a normal to all of these surfaces. So if I act the stress on the normal, this quantity in here is S acting on N. Does this look familiar? This integral? Integral S N dA. This is this is indeed total force total force acting on the surface area. But we have dealt with these types of integrals when we were talking about divergence theorem back in chapter 1, that some tensor acting on the normal integrated on a area of a body, surface area of a body is equal to divergence of tensor integrated over the volume of the body. So both of these, this is directly from the divergence theorem. So we'll apply divergence theorem to this integral, and we get integral over the deformed volume of the body of divergence of stress, Cauchy stress, plus body force times dV equal to 0, vector. And so this is a relationship that will ensure that this part of the body is in equilibrium. Now note that when we started writing these equilibrium equations, we did not say that this was some specific part. This could be any arbitrary part of the body, no matter how big or small. The integral of this quantity must be equal to 0 for any arbitrary deformed body, any part of an arbitrary deformed body, which means that this condition, this integrand itself must be 0, otherwise it won't work, right? The fact that this integral is 0 for any arbitrary body means that this integrand must be 0. Only then it will, integrand must be 0 for all points in the body. Only then can this integral be 0 for any arbitrary volume. So that gives us the condition that divergence of stress plus body force density equal to 0 at all points x in the deformed body. So this is a very fundamental equation of equilibrium that you must understand. This equilibrium equation is no different from this equilibrium equation. Keep in mind that what you have learned in undergraduate problems, sum of forces equal to 0, this equation, divergence of S plus B equal to 0, is that equation for a deformable body written at any point. So this equation is saying Newton's first law must hold at every point in a deformable body. Okay, very important relationship. So we can also write this in an indicial notation. But before I do that, let me ask you this: is this a scalar equation, a vector equation, a tensor equation? What is this? Vector equation, right? Clearly, body force density is a vector. Right hand side 0 is a vector. Divergence of a tensor would be a vector. And this vector equation is saying nothing but sum of forces should be equal to in x, y, z, or z1, z2, z3, x1, x2, x3 directions. So we can write this in terms of indices as well. That would be partial Sij xj. That would be divergence of stress, the ith component, plus Bi equal to 0. right? So here note that I is the free index, and maybe I hate writing this I on the zero, but I'll write it in red. Uh, I is a free index. It must occur on both sides of an equation. All this is saying is that the ith component of the zero vector is also zero. Okay. I is the free index, so it must occur on both sides of the equation. J is the repeated index here, so there's really three terms here. Partial of Si 1 with respect to 1, 2 with respect to 2, and 3 with respect to 3. All those three get summed up, plus B1 equal to 0. So, and then of course you write that for the three directions. Another important point to note, these derivatives are with respect to the deformed coordinates, not with respect to the undeformed coordinates. These are not partial zj, partial xj. All right. Um, so to maybe give you an alternate way of understanding where this equation came from, we know that it came from sum of forces equal to 0, and divergence theorem gave us this equation. But there's an alternate way to come up with this, somewhat relatively crude way. But what we'll do is we'll set up that exact same body, and now we are going to take the size of the body to be tending to 0. So it is an infinitesimal neighborhood of a point. We have delta x1, delta x2, and delta x3 as the sides of that cube type neighborhood. I've of course marked the 6 faces 1 through 6. Each face has its normal plus minus e1, e2, e3. And on each face, I'm drawing these red arrows also. So the normals are in green, but there are these red arrows, which are the traction vectors acting on those 6 faces. And clearly, you can see that those traction vectors need not be along the normal, right? So these traction vectors I know are obtained from stress tensor acting on that normal. So this T1, T1 is just saying that the traction vector on face 1 is obtained by stress tensor acting on the normal minus E1. Similarly, T2, stress tensor acting on the normal plus E1. Now, what we'll do is again write equilibrium equation. So to find the total force acting on all of these 6 faces, I would have to first try to express the tractions on the 6 faces, which I did here. Nothing but stress acting on the corresponding normals. What I'll also do is try to relate the tractions on the opposite faces. So I'll try to relate traction on face 1 with traction on face 2, which are separated by a distance delta x1. So if you write stress at the point x2 in terms of by expanding it as a Taylor series, then this can be approximated as this. So the stress at point 2 can be expressed as stress at point 1 plus derivative of stress with respect to x1 times delta x1, right? This is nothing but the Taylor series expansion of stress at x2 around the point stress at x1. That's all that this relationship is. And so this gives me the stress, an approximate stress at the center of the face x2 acting on the normal vector. That would be the traction on the face 2. Similarly, I'll do that for faces 4 and 6. And if you sum that all up, you'll see that Sx minus E1, Sx plus E1, they will cancel out. What I'll be remaining with would be partial x1 times delta x1, partial x2 delta x2, partial x3 delta x3. And when you multiply these tractions with the areas, you get x1, x2, x3 common out, and you come up with the exact same relationship, divergence of stress plus body force equal to 0. So this is an alternative way, maybe something that you might be more used to, where we are again doing the sum of forces explicitly and trying to figure out what would be the condition for equilibrium of a point. Okay. Any questions on this?
Won't it be the exact opposite of it?
Say that again?
Just minus T of E1
Yeah.
would be minus T of minus E1.
That's correct. But we are not trying to relate T of E1 to minus T of E1. We are trying to relate T2 with T1. These are two different points. Even though the body is infinitesimal, these are two different points. And in the limit, you are right that they would be equal. But we are not. Okay, so maybe I'll take a. If I have x, some function of x that looks like this, then there is a slope at that point, right? And let's say the point that I'm looking at is x0, and I want to find its value at x0 plus delta x. So the function value at x0 plus delta x can be approximated as f x0 plus df dx at x0 times delta x, right? But that does not mean when you say that the value on this side of of this point and value of this side of the point in terms of tractions, it would be in the opposite direction but same magnitude. But even though the value to the left and the right of that point is the same, the slope of that point is not zero. It's the slope, the derivative of the stress that is what we are talking about. Okay, maybe what we'll do is uh, talk about this offline if that's not clear. That's not clear, but uh, what I was trying to say here was that we are not really comparing tractions directly with tractions directly on either side of a face. We are trying to find the derivative or of the stress, how it varies at a particular point. That's why we get this equation. Um, all right, so that's just the sum of forces. If we similarly now look at sum of moments, we again will go to the same free body diagram. Some of these tractions on all of the surface, on the deformed surface, and the body force in the deformed body. This is the free body diagram that I'm considering. I need to take moments about some point. So what point should I choose? Center of the body, or does it matter what point you choose? No. So of course with equilibrium, when we did sum of moments about some point, the location of that point did not matter. It could be inside a body, outside a body, wherever. So we pick some arbitrary location to be the origin, O, and I'm going to do sum of moments about that point. So can you take maybe 30 seconds and try to write what the equilibrium equation would be? Very similar to this that we wrote up here. This was the equation that we wrote for sum of forces equal to 0 for the same free body diagram. What I'm asking you to do now is to write the sum of moments equal to 0 for that same free body diagram. Note, and this is a finite sized body, not an infinitesimal body. All right, so maybe you've had a chance to think about it, at least if you weren't able to write the equation just yet. But let me ask you this. When you had a three-dimensional body, when you were trying to do sum of moments equal to zero for a three-dimensional body, what expression, how did you calculate moments? If I have some object like this, let's say I'm doing moments about one corner of the object and there is a point load, point F force vector acting on at a different corner. How did you do moments of that force about this corner? About a point, r cross f. So, and that's exactly what we are going to do. So we are going to take some infinitesimal area anywhere on this surface. I know the total force acting on that infinitesimal area would be T n dA. That's the infinitesimal force. If I take x cross product with that and integrate it over the deformed area, that should be equal to the moment due to all of these surface tractions over the entire body about this point O, right? X cross with T and dA. That's moments. I'll remove this parenthesis as well. And to that, I need to add the body forces. So B times dV, that's the infinitesimal force. B is the body force density, so multiply with dV gives me an infinitesimal force. And integrated, oh, I need to take the moment of that force. So X cross with that infinitesimal force computed or integrated over the deformed body would be the moment of the distributed body force about that same point. And indeed, all of that has to be equal to the zero vector. Moment is also a vector. Right? So that equation is the governing equation for this deformed body equilibrium of moments. Question, Joe?
That's a small v, right?
You're right, sorry. I have to be using small dv. Big V is the one that we are using for the undeformed volume, so it's a small v. We'll go through the process by applying divergence theorem to this term, very similar to what we did for the forces. But rather than going through the algebra, I'll let you make sure that this algebra is correct. And when we apply the divergence theorem, we come up with something like this equation. Now, the second term of this equation is nothing but divergence of S plus B equal to 0, which is equal to 0 because we said sum of forces is 0. That leaves only this term. And this term must be 0 for any arbitrary body. So therefore, the integrand of this integral must also be 0, which gives me this condition. This is the condition that says it's in terms of this Kronecker delta. So let me ask you this. First question, there's epsilon ijk sj sji equal to 0. So how many terms are there on the left hand side in this equation? Even though there are 3 indices, one of them is a free index. Right? So k is a free index. Typically, I would also write 0 of k, but I did not do that here. So ij and ji, of course, are repeated. They are summed up. So this is a sum of 9 terms on the left, and that's equal to 0. So, but keep in mind that epsilon ijk, a lot of those entries are 0, and we'll see what the consequence of that is. So I'll take that equation, epsilon ijk sji equal to 0. If I switch the order of I and j in the epsilon, what happens? Minus, right? Epsilon ijk is equal to minus epsilon jik. So from this equation, I get that this equal to 0. Now I'll do an exchange between I and j. I will replace j with I and I with j. So the sign should not change. And what I get is epsilon ijk sij equal to 0. and negative because of this negative. So since I have these two equations, if I add them together, epsilon ijk would come out, and I would get Sji minus Sij equal to 0, which simply says that Sij is equal to Sji. That S tensor should be symmetric if the body is to be in moment equilibrium, meaning that the stress tensor field at every point in the deformed body has to be symmetric in order for the body to be in moment equilibrium. So sum of forces says divergence of S equal to B. Sum of moments equal to 0 says stress tensor should be symmetric. And those are the two conditions that we need to really enforce to be able to say that a body is in equilibrium or not. And finally, this allows us to state that structural mechanics problem that we've been building up towards. In order for a given structure that has some boundary conditions, some loading specified, some material properties, we have not gotten into material properties yet, but we'll do that shortly. So in order to be able to do that, we have to be able to write the conditions that for equilibrium to hold would be that which are called governing differential equations, GDE, divergence of Cauchy stress plus body force density equal to 0 at every point x in the deformed body phi of B. Similarly, S is equal to S transpose at every point x in the deformed body. And the Cauchy stress traction relationship T sub n has to be equal to Cauchy stress acting on the unit normal has to hold at every point x on the deformed surface of a body. These are the three equilibrium conditions that must hold at every point inside the body are the first two conditions, and every point on the surface of the body is this third condition that we are talking about. Now the third condition, we'll take a look at it a little bit more closely. The surface of the body itself has two parts. This phi of A has two parts, phi of A sub D and union with phi of A sub N. What is A sub D and A sub N? A sub D is the part where displacement is specified. Okay, you cannot specify external forces at a point where displacements are specified. If I give you a cantilever beam fixed at one end, you cannot say that I'll also apply some forces at the fixed end. When you apply a tip load, what are the reactions at that point? Because the forces at the fixed end are given by the reactions that are due to the applied load. Okay. So on this fixed end, we have unknown reactions typically, and those unknown reactions are also obtained, are obviously distributed forces. They are obtained from S acting on N, which is the N to this part AD of that boundary. And similarly, the rest of the body where displacements are not specified is called A sub N, where I'll also comment here. D stands for Dirichlet. This is more of a partial differential equations terminology, PDE terminology, but this is very common in mechanics as well. And N stands for Neumann. So Dirichlet boundary is the boundary where displacements are specified, and Neumann boundary is where tractions are specified. So in this particular problem, it seems that I'm specifying tractions only on this part. Does that mean that only this part is the Neumann boundary, or is the whole surface boundary? A sub n, I have marked that as the whole rest of the surface of the body. Since I'm not specifying any traction out here, the traction simply is 0. But traction is, so one way to read that would be that the traction is specified on the entire rest of the body, traction being 0 where it is not given, and traction is non-zero only in this part where we are given. So that gives those conditions two conditions of equilibrium of forces and moments everywhere inside a deformed body. Traction condition, traction stress Cauchy relationship at every point of the boundary of the body, whether it is unknown reactions or external forces. This condition must hold. Okay, that gives us the conditions to be satisfied for equilibrium. So, so up until now, just to lay some context here, if we are given this type of a problem, that here's a body, find its deformed configuration, find the map phi that this body would undergo if this was the applied forces. To do that type of a problem, to find the map of a deformation body, that what we would need is a certain set of equations that we are solving for. The unknowns that we are solving for, the displacement, strains, and stresses. We have been able to relate displacements and strains till now, correct? That was in kinematics. We have been able to relate stresses to equilibrium. These are conditions that must be satisfied. All that remains now really is to relate strains with stresses. And once we are able to do that, we'll be able to solve problems like this, where the question says find the deformation of this body given these loads, given these boundary conditions and material properties and so on. All right, so we'll stop here and we'll get into that probably next lecture.